Recording started. So yeah, so I think previously we were looking at things like the performance gaps. This was looking at energy use in buildings, and previously energy and reducing energy emissions was a key part of building design, again, certainly in the UK. More recently, we've been thinking about life cycle thinking, embodied carbon, net zero carbon, those sort of things. And then certainly circularity and regenerative practice is going to be the focus for the next few years. Thinking about kind of circular resource use, going beyond doing net zero harm, but actually doing good to the planet. So back to our 5 myths. So our first one, it's better to knock down an old inefficient building and rebuild it. Actually, what we found is that refurbishing first and using that approach to reduce energy and minimize upfront carbon can be much better than knocking down old inefficient buildings, basically using the materials and resources that we've got in a more efficient way to improve existing built assets. When we say sustainability costs money, a lot of the time when you are designing something with a low carbon footprint, for example, or low embodied carbon footprint, you're basically saying put less stuff in the building. And less stuff means less expenditure, less cost. So actually building less can be more sustainable and lower cost, and is generally a bit more sustainable as well. Net zero carbon, a lot of people think that you just pay for offsets, but actually there's a whole approach. You need to reduce your impacts first. And there aren't enough offsets to go around fundamentally. We can't plant enough trees or capture enough carbon from the air to like completely mitigate the impacts that we're having on the built environment. So most pathways to net zero carbon mean that you have a 90% reduction in your carbon emissions first, and then you can offset the last 10% potentially. And then sustainability is just box checking. So actually, when you have a sustainable approach that's effectively implemented by teams, fundamentally it makes better buildings. Thinking about the social side of sustainability, people use our buildings, we design for people. So we need our buildings to be socially sustainable, enjoyable places to be, healthier environments. And so if you get all that right, then you've got a more sustainable building, and it's not just box checking, it's actually a better place to live. And finally, cutting down trees for construction is bad for the planet. Possibly slightly controversial one, but I'll caveat this in a lot of ways, saying that it needs to be sustainably forested, so sustainably sourced timber. But actually, if you're considering using structural materials such as steel, concrete, or timber, then actually timber and bamboo are probably the only renewable ones that you've got. So obviously, you want to use the right materials and the right application, but definitely using trees for construction, as long as they're replanted and it's used in a sustainable way and used efficiently, can actually be a net kind of benefit when compared to using concrete or steel. So that's the kind of like headline for sustainability. And if you've got any questions on any of this, then feel free just to stick them in the chat and we can come up to answer them in the end. Now I'm going to talk a little bit about some of the key principles that you can use and design strategies that you can use to minimize the impacts on your projects. So focusing in a bit more on embodied carbon, because this, as I said, is the kind of focus for the industry at the moment, and this is where a lot of structural engineers have the greatest impact. The ISRC and PAS 2080 have got some great guidance on how to do this, and fundamentally it comes down to basically using less stuff in our buildings, designing to use fewer materials, and then finally specifying lower carbon and offsetting at the very end. But they're kind of like quite a small piece of the picture. It really just comes down to reduction first. Digging into the details of that, there's this hierarchy which you might have heard of, which basically starts build nothing, build less, build clever, build efficiently, and then minimize waste. And in terms of on projects, build nothing is very much about challenging the brief. So it's trying to understand, is construction actually the right answer for my project? If you have a client coming to you saying, I would like a new building because of X, Y, and Z, you have to kind of go back and actually challenge, is construction really the thing that you want to solve this particular problem? Could it just be reconfiguring the way you currently run your business, for example, to use better, use the space better, for example? Or yeah, like it's kind of like testing. There's usually like a wider problem which is trying to be solved by construction. It might be that there's some sort of investment portfolio. And actually, there's other ways that you could potentially solve that problem that don't result in construction and therefore carbon emissions. So it's a bit of a tricky one. And I think a lot of our industry is very much focused on effectively us getting paid when things get built. So it's quite tricky to kind of change that paradigm and shift that around. But build nothing should certainly be the first thing that you approach on each project. The next one is build less. So can we actually get away with repurposing existing buildings or refurbishing existing buildings or reusing existing assets maybe from other projects? How can we maximize the space that we've got available? In the pandemic, we've seen a big migration of people moving from the office and kind of living out in the suburbs. So now there's actually potentially quite a lot of office spaces in city centre locations, which is basically underutilized. At the same time, we've got a housing crisis. Young people can't afford to buy houses, at least in the UK, and I'm sure similar places overseas as well. So, you know, is there an option to switch some of those office spaces that were previously zoned for commercial to residential use instead, refit those? Now we're kind of using the assets we've got in the right way, we're repurposing them for something that's more valuable, but without building a whole load of new buildings or knocking down existing ones. Build clever is basically around appropriate structural configurations, coming up with the right design criteria, and designing things efficiently, using the right materials in the right places, getting rid of things like transfers, removing basements from your design. All of these things use a lot of materials that basically don't necessarily need to be there and can potentially be avoided by just reconfiguring the building in a different way. Build efficiently is the next one. So how do we use our materials as efficiently as possible? So don't design to 70%, 80%, 90%, design to 100% or near enough 100% utilization for everything. There's enough safety factors already built into the codes. We don't need to add our own ones on top of that. And then it's using carbon efficient materials as well. So how can we make the right kind of specification choices, or use renewable materials like timber if that's an option. And then finally, minimizing waste. So prefabrication is great. If you can use if you can build your building in like an off-site environment, there's going to be much less waste on site, and just generally kind of good construction practice like electrification of construction services like plant equipment, reducing fuel use, reducing excavation. All these kind of things will have fairly substantial impacts on your carbon reduction. So that all kind of sits in the use less stuff bit of this triangle. And then the next two bits are specify low carbon offset, and I'll talk a little bit about those in a second, kind of go into the details of how you might do that on a material basis. Just to give you some examples, so top of this hierarchy or near the top, build less. This is a study we did recently on the carbon impacts of refurbishment options versus new construction for a development in London. And it turns out that when you factor in the operational carbon, so that's the operational bit here is in blue, and then the embodied carbon for future refurbishment is in light orange, and then dark orange is kind of the impacts of basically building a new building or doing some of the new refurbishment bits. So this is not just the structure, this is the whole building, because we're trying to look kind of beyond the scope of structure potentially. And the scale here, by the way, if you're not familiar with it, this is carbon dioxide, or kilos of carbon dioxide equivalent per meter squared of floor area. So it's kind of normalized. So the total amount of tons of carbon which are emitted as a result of all of the construction processes and operating the building and everything else, and then divided down by the square meterage of the building so that you get like an average that can be compared building to building. I'll go more into the details of life cycle assessment and how to measure carbon and things like that in the second lecture, but just to give you a bit of background to it. Basically, less carbon is better. That's the key thing. So the one on the left is basically if we kept running the existing building, the building was using gas boilers. So there was no upfront emissions because we weren't adding anything new to it. But actually, we're still going to need some sort of refurbishment and repair and things like that in the future. That's why we're going to need a new facade. There's going to be some more fit outs that happened over the years. So there's some upfront emissions there. But the biggest bit of the picture here is obviously the operational emissions. So it's burning gas. And gas over 60 years has a very significant, like for heating the building, has a very significant environmental impact. So the first move was to basically move off gas onto the electric grid. And in the UK, we're quite lucky because the electrical grid is rapidly decarbonising. We're switching to renewables, and in fact, by I think it's 2035, potentially the grid is going to be carbon neutral when you start factoring in carbon capture and storage that's in the pipeline. So if you can switch all of your building systems onto the electrical grid, then that's the kind of the biggest move you can make first. But in doing that, we needed a lot of new building services, and there was a small extension as well, which we're going to add, and there's a lot of new refit as well. So actually there was some upfront carbon emissions, and then that future repair and replacement doesn't go away. And then as you kind of go along the spectrum, you get right along to the kind of full new construction. So you'll see that the operational footprint is reducing each time because we're putting in more efficient fabric, we're putting in more efficient building services, and there's an upfront carbon cost to do that, but it reduces the whole life impacts of running that building. But actually the gains are quite marginal. And remember, this is happening over 60 years. This stuff in dark orange happens immediately. So as soon as you finish construction, all of that carbon has been emitted. So clearly the better option here, both in the short term and also in the long term, is actually to keep reusing the existing assets. And you find this quite a lot whenever you do these sort of whole building studies. So the key thing is refurbishing uses less material and has lower whole life impacts. The second bit, which I want to raise, so this comes under build clever. The structures are over-designed. If you look at the different rules of thumb and different space planning rules for the number of people that are assumed to be in this typical office building, and this has been around for a while, this study, I think this is the Mycon study back in 2017 or something. When you design your ventilation, you assume there's 3,000 people in the building. When you design for space planning, so enough room to move around and use the office space, you assume there's 3,750. When you design for fire, you assume there's 7,500 people in the building all trying to get out at the same time. When we design the structure, we assume there are 85,500 people in this building. Obviously, there's lots of safety factors and everything else in there, but this is without adding that kind of extra, 10-20% fudge factor that people like to include just to, so they can sleep at night. This is really significant, and if we can reduce the loading in our buildings, because there's no particular bit in the building regs in the UK at least that say you must design for this load. It's only defined by the Eurocodes. So if we can kind of push loadings down and at least push back against clients that want to design for very high loading allowances, then we are going to save carbon, and we're going to reduce the material impacts of our building. So yeah, don't over design. And then finally, you can go into kind of refining the design as well. So, again, this kind of sits in the build clever bit of the hierarchy. If you can reduce your column grids, then you're going to use less material, which is also going to have a lower environmental impact. So moving from a 9x9 grid down to a 6.5 by 6.5 grid, even if you keep the same material, like you don't have to necessarily switch from concrete to timber or anything like that, you're going to save a significant amount of material impacts from your building. I've got all the sources for here as well, and I'll highlight them at the end too. So now we've talked a bit about design strategies that you can use, and there's just a few kind of headlines. I'm sure there's plenty more alternatives out there. So now we'll talk a little bit about what can we do when it comes to specification. And I've put that at the bottom of the triangle, so the specify low carbon bit after you use less stuff, because there's a lot of caveats around this. So concrete, obviously, great material, fantastic for foundations, very durable, used a lot in construction. And I think a lot of people will feel that if you can just specify high amounts of cement replacement, most of the carbon emission in concrete comes from the cement that's used, a little bit from the steel, and then some from the kind of construction side of things and waste, transport, admixtures, all that sort of stuff. But most of it is the cement. This is taken from the iStruct. So ideally, we want to kind of reduce or replace that cement. So if you can specify lower strengths, then you've reduced the amount of cement in there. If you can put a cap on your specifications to make sure that there isn't just a minimum cement content, but there's actually a maximum cement content as well, then that means that contractors and those building the buildings aren't going to be adding in more cement to maybe make it more workable or to make it cure quicker or gain strength earlier. So you want to be kind of like being careful to cap that as well to make sure they're not over allowing for cement. And then finally, once you've done that as much as you can, then you want to be looking at cement replacement. So that's things like GGBS and PFA, which are kind of old hat now. The ICE has got a great guide on this recently, the kind of low carbon concrete working group. So I definitely go to that in the first instance. But fundamentally, there isn't enough low carbon cement replacement to fulfill demand. So if you're specifying 50%, 80% GGBS on your projects, all that means is you're basically just taking the limited supply of GGBS or cement replacement that we have out of the global supply and putting it into your building, but somewhere else is going to suffer, and potentially that GGBS could be better used, for example, to keep the temperature down on a really large pour, which is going to have a long cure time. So yeah, it needs to be used appropriately. Steel is the other big structural material that has a high impact. So the alternative to the basic oxygen furnace, blast furnace process for steel making, which uses a lot of raw materials, is to use the electric arc furnace process. So you can go from I think something like 20% recycled material maximum for the blast furnace approach, up to like nearly 100% recycled content if you use it, if you manufacture it using an electric arc furnace. And that reduces the carbon emissions down by a factor of 5 by doing that. So you're cutting your carbon rate from something like 2.5 kilos of CO2 per kilo of material down to 0.7. But again, there's a limited amount of scrap. So if you're specifying electric arc furnace produced steel or 100% recycled metal, all of our scrap steel is already reused in this way. So global scrap is already kind of going back around the loop and being used in this process. So again, you're not really actually like solving the problem here with your specification. You're actually just basically buying up all of the lowest carbon bits of steel that are around, and then there's suddenly no more left for potentially more appropriate uses. So again, you need to actually reduce the amount that you need in the first place. And then finally, timber. So timber's another good structural material, and obviously it's renewable. It's a very low carbon resource. Critically, though, it's a finite resource. All the trees that we have planted to get to net zero carbon by 2050, all the trees that we will need to get to net zero carbon by 2050 have already been planted. We're not going to be able to plant anymore. We can't add loads of areas of forest to the world. So we have a limited amount of timber to use, and crucially, it must be sustainably sourced. We can't be using timber from illegally forested areas, because that is obviously going to prevent any future effects of those trees basically absorbing carbon from the atmosphere. So there needs to be some kind of continuous replanting as well, and making sure that that timber is used appropriately at the end of its life, so that the carbon that's locked away in the timber when it goes into a building is not then re-emitted once the building gets demolished by accident. Reclaimed materials is another one that you might not have considered. So they're obviously very circular. So if you have a project which you know is being demolished and you think there's potentially some materials that could reuse from it, then that fits well into the kind of circular economy narrative. They're very low carbon and potentially low cost as well. There are more challenges around using reclaimed materials. So the key ones are probably things like storage. Once you've disassembled your building, what do you do with the materials that you're actually storing? How can you make sure that they're being handled appropriately? How do you test them? How do you make sure they're being warranted and insured? The ISTRC has got an excellent guide on the circular economy in practice for structural engineers, which I think is coming out this month. It's sort of been in the pipeline for a few months now, so hopefully it'll be coming soon. But this is, I think, going to really kind of change the game when it comes to circularity in construction and circularity for structural engineers, by answering a lot of these questions and giving you approaches that you can use on your projects. But reclaimed materials are definitely a good choice if you have the availability and you know of a project where you can use them. I'm just going to go through a few project examples then for sort of the last 10 minutes or so. A few things that I've worked on, which I think probably fit well into this kind of sustainability narrative, but again, I'm sure there's better examples out there. So the first one is this housing development in Lombok in Indonesia. So a few years ago, there was a major earthquake in Lombok, which caused a lot of the kind of low quality masonry and concrete buildings to collapse, unfortunately. Did a lot of damage, displaced, I think, hundreds of thousands of people. And we were fortunate enough to be involved with a charity that was involved in the reconstruction efforts there, and really wanted to kind of use this as an opportunity to change the paradigm of construction from using kind of materials that are perceived as being kind of high quality Western ones to using a material that was actually more locally available, like bamboo, and designing it in such a way to make it earthquake resistant and hopefully sustainable. So we came up with this design and actually built a few template houses. It's got concrete foundations, steel connections, and then a bamboo frame. But really, we kind of wanted to focus also on the kind of wider sustainability benefits. So there was a sustainable model that kind of went with this, that basically enables people to potentially grow their own bamboo, use it for things like food and for furniture in the short term, or crafts. And then over 5 years, they're basically growing the materials that they can use to potentially then use to build additional houses. And then these ones are still there, so they're kind of there as like a template and a learning center. So there's a kind of economic value to that. So you're kind of growing the bamboo for local crafts and construction. There's a social value. I mean, obviously the building itself can be used, but there's local construction employment and skills training there. And then obviously the kind of environmental benefits of using bamboo. It's a renewable, fast growing, and acts as a carbon store. Again, you have to use it in the right way, and actually Bamboo treatment and durability is really key. I think if we were to do this again, we probably cover up a lot of the bamboo structure so it lasts longer and isn't damaged by UV and rain over a number of years. But it's a good example of basically how you can kind of use structural engineering and buildings to create a kind of wider sustainable value for a community potentially. Another project that I've worked on recently, this is the Evo building at the Didsbury Technology Park. It's being sold as the world's most sustainable, the UK's most sustainable workplace, and it's targeting net zero carbon both in construction and in operation. For this project, which we're working on for a few years now, we really kind of like tried to change the paradigm of construction from being an architect comes up with a form, and then the structural engineer and services engineer tried to sort of fit in around that, to actually what would be the optimum mechanical solution for this, what would be the optimum structural solution for this to really minimize the impact of the building, maximize the space, and then how can we kind of use those concepts to mesh them together with an architectural concept that works as well. So it really was very much an engineering driven project to create the lowest embodied and operational carbon footprint possible. It's got a glulam frame with cross-laminated timber floors, so glulam downstand beams and columns. There's a concrete core, which was kind of necessary for stability and fire reasons more than anything else. And then piled foundations. Again, we kind of looked at options for shallow foundations and things like that, and decided the piles were probably most appropriate for this building. So the timber used in here obviously is sourced from sustainably managed forests. There's a lot of carbon basically locked away in that now, so the building kind of acts as like a temporary carbon store whilst the building is there. Yeah, I think it's like generally quite successful. This is up in Manchester where I'm based, and I think it's going to be built. It got planning recently, so it should be built hopefully in the next year or so. And then finally, I'm going to talk a bit about the Co-op Green Store. So the Co-op is an organisation in the UK which has got very kind of strong social values. But they realized that actually a lot of their developments are only kind of around for about 25 years before they stop being commercially viable. So they're building these new buildings, and then actually 25 years later, they basically don't need to be there anymore. It doesn't work. So really, we're trying to switch the focus for this on what if we were to design a building that only needed to be there 25 years, and how could we design it so it could be easily disassembled and moved, minimizing the impact on the site after it's completed. We tried to remove all the concrete in this building. So we used screw pile foundations, which are basically metal helical piles which screw into the ground, and then crucially can be taken out, moved to another site and reused somewhere else. It's on a very short pile grid as well, just to keep the floor as efficient as possible. We used a lot of off-site manufacturing techniques. So it uses panelized timber construction throughout, and it's designed for disassembly as well. So yeah, like I said, we use screw pile foundations that can be removed from the ground, but also all the different modules of the building and all the different components can be basically just unscrewed or unbolted and potentially moved to a new location and then reassembled to make the same store, but in a different location. So there's a kind of circularity benefit to reusing this thing. Yeah, so the idea was to kind of create this fully demountable building. And the way we actually did that was to start with this baseline store, which is the kind of the functional one, which they were quite happy with. The design was already quite efficient. It was like a steel frame with concrete foundations and timber roof trusses, and then switch that to this panelized modular timber green store instead, which I think is a bit more efficient. So that was 35 minutes. So I've kind of whizzed through that, 5 minutes to spare. I'll just go through a few really valuable resources if you do want some more information on how to do sustainable structural design. The iStruct's sustainability resource map is really an excellent starting point. There's a link to it in the bottom corner here, which we can share around the links and stuff afterwards as well. But really, like for any of these topics, every single one of these is a link to a video or a resource or a piece of guidance. So if you've got any questions on any of these topics, then absolutely use this as your starting point for that kind of like knowledge search. Yeah, it's a really useful resource, and I know that the sustainability panel and the climate emergency task group have put a lot of effort into curating this and improving it over the last couple of years as well. So hopefully it's a good starting point. And then there's a few bits of key information as well. So a lot of the examples I've taken from here are from the iStruct's guide Design for Zero, which is an excellent book and really like kind of digs into a lot of the strategies and gives you a lot more detail on some of the stuff that I've been talking about today. If you want to know a bit more about carbon in particular, then there's the Embodied Carbon Primer by Letty, which gives you a kind of overall picture of carbon emissions in construction. And then the iStrategy's How to Calculate Embodied Carbon Guide as well, to actually kind of go through the specifics. Like I say, I'll cover this stuff, the life cycle assessment and carbon emission reduction in a lot more detail in the next session. So there's more just like kind of headline over the design strategies. So that was all from me. Quite a short one, but hopefully you found it interesting and relevant. And yeah, I'd be very happy to take any questions or have a discussion now.
Hi, Tom. I have a quick one. I don't know how we're doing this, but I just thought I'd unmute and go first.
Go for it.
Thank you for that. I thought that was a really good presentation, and I'm aware that Ramboll are one of the best at doing this. So happy to hear someone from the inside. The 5 myths of sustainable construction that you debunked, I was most interested in, because I thought that it's a couple items there that no one kind of talks about, and you've managed to talk about them and debunk them. I just wanted to know, in the case study that you presented with the timber building, the EV0, what targets did you use for that? Were you following Letty? I know Letty's more for the English audience members rather than the Caribbean ones. But I just kind of want to know, what targets did you follow? Because there's a lot of discussion globally, I think, as to what we should follow, and from just what is the embodied carbon numbers we should use for a particular material. There's even debate about that. So what are your thoughts on that? And what does Ramboll think about that, and what do you use? Like, do you use the ICE database, for example, or do you follow the guidance that you just put there? Which is very good guidance, to be honest. The iStrategy guidance is very good, and I've been to many lectures with Will Arnold, and you seem to be exactly in line with what he's been saying for the last several years. So, I don't know your thoughts.
Learn from the best. No, it's a great question. I think like carbon targets are useful, but we've got to remember that every time you're trying to measure the impact of the building, this is just a tool to tell you a number. And if you tell you a number that's above or below the target, it kind of doesn't really matter too much, because what you really want to be doing is using that to make informed design decisions. You want to be reducing it. So for your specific projects, particularly if there's no kind of good industry guidance available that says, buildings based on a lot of existing data sets are, let's say, 500 kilos of carbon per meter squared, or 200 for your structure or whatever. If you don't have that information available, then really you should be focusing on a reduction target instead. So say, okay, at the start of the project, maybe Reba stage 2, we'll do a kind of initial stab at the design. We'll come up with like our kind of business as usual, what we normally do. Use the iStrat tools to measure the impact of that, and then set a target that's maybe something like 30% lower than that, or 40% reduction on that. So you use like an old version of the design as like your baseline, and then say, okay, how can we improve that? If you use these tools and techniques to basically measure the impacts of your buildings, then it will kind of point you in the right direction as well. So you'll be able to say, okay, well, it looks like the foundations are the big item on this project, or it looks like the steel frame is really high impact, and then you can focus your kind of optioneering around those specific things that are identified by that carbon assessment. But yeah, fundamentally, it's like you don't want to just hang up on a number and say, oh, okay, well, we said 500, we're at 498, so job done, we don't need to do anymore. It's really very much like a kind of continuous process to keep pushing at each stage to try and reduce the impact each time.
Yeah, I guess it serves more as a guide for the design team, but I guess until these things get mandated in any country, there isn't an obligation to follow that, other than if it's client driven, that you have a client that's interested in helping, in tackling this climate emergency. So I suppose it starts from the top.
Yeah, definitely. And if you're using the iStrat tool, I mean, obviously things like the transport distances and material profiles are going to be generally kind of UK specific, I think.
I was going to say, because if you're importing something into Barbados or Trinidad, for example, it's coming across on a ship. and every island specializes in different things. So for example, Barbados, we manufacture cement, aggregate, and sand. So everything predominantly concrete. In Trinidad, they use steel for more things because they actually manufacture that there. We'd have to import steel from Trinidad, for example, if we were doing steel building in Barbados. So the tool, I guess we have to find a way to customize the tool to suit the Caribbean region, I would imagine.
Yeah, the transport impacts aren't as significant as you might think a lot of the time. I think when you're using kind of bulk materials like aggregate and concrete and things like that, which have a very high mass but a very low carbon footprint per like kilo of that, then the transport is important. So it makes sense to kind of source your concrete from like a local concrete batching plant, for example, rather than import it. High intensity materials like steel, actually it makes sense to kind of pick the ones that are using the right production method, because the carbon impact of shipping steel from China, for example, rather than using stuff that's made locally in like let's say your options were ship steel from China that uses the electric arc furnace process, or use steel that's manufactured locally using a basic oxygen furnace process. The one from China is probably still going to be lower carbon because most of the impacts are in the steel production process. It's still the energy used to actually manufacture the steel in the first place rather than the transport to get it to the site. So yeah, but again, like, you know, the carbon rates, you can kind of, you'll get like an answer on it, and it might not be particularly accurate, but the key thing is that you can use it to then say, okay, well, if I change this steel to come from this other location, or if I reduce the amount of steel by 20%, then I can demonstrate that I'm going to save about this many tons of carbon. So it's again, it's a tool to kind of inform that decision process, and it just has to be accurate enough to enable you to make that informed choice, rather than necessarily being like, you know, this is the actual number of, this is the actual amount of carbon that's going to be emitted.
Okay.
Yeah, hopefully that helps. That was the question.
No, yes, thanks.
Cool.
Tom, I have a question. I saw something very interesting in your presentation, and this slide challenged the brief. There was something like 3,000 people for ventilation. It went down to about nearly the same thing for planning. The amount of people was doubled for fire. And then it was a huge value for structure. Yeah, that side. So there was a huge value for structural design in terms of people. Are there any committees or persons involved in terms of people who write the codes to kind of change that? Because a lot of people, especially in the Caribbean, where you have to go for statutory approvals, you're bound by a design code, and it's very stringent in some cases, so you have to follow it exactly 30.
Yeah, yeah, it's a great question. I think there's certainly a lot of pressure in the UK to change things like the Eurocodes, to potentially have a clause in them that basically says you shall design for this amount of utilization and no more. So the main issue here is not so much necessarily the codes, because the codes are based on you know, kind of statistical measurements, and actually by designing our buildings, they are generally safer. But this is the kind of natural outcome of putting safety first, instead of material efficiency necessarily. So yeah, I think there's kind of like there are pressures to kind of like change the codes, but I wouldn't expect them to make any kind of significant differences to this number. The key reason I bring this slide up is to address the issue that we see often in design teams and design processes, which is that at maybe the early stage of design, people basically add in their own safety factors. So you design stuff to 80% because you think, well, you know, I need a little bit extra in there just in case, you know, the architecture changes, or in case the contractor does something wrong on site, or something like that. So you add like another 20% in there. But every time you're doing that, you're adding another 20% material, and therefore another 20% carbon potentially, or you know, other material impacts. So it's the main point of this is to get across that like that kind of additional extra safety factor that people put in for their own kind of peace of mind is basically not necessary. There's enough safety factors in there when it comes to material safety factors, load safety factors, and the actual kind of code design values of say 3 kilonewtons per meter squared are very unlikely to ever happen across a whole floor plate, potentially never even in a localized area for the entire building lifetime. So it's a very kind of like safety first approach to designing things. So with all that in mind, the probability that you're if you design that for 60,000 people, for example, the probability that there's ever going to be 60,000 people in that building is pretty small. So it's just kind of being aware that this is kind of the framework in which structural engineers operates, I suppose.
Okay, thank you for that. Are there any other questions?
We've got one from Chizzy. Did you want to come on and say it, or shall I can read it out? So it says, timber is a renewable material. However, there are also upfront carbon emissions involved in the production of engineered timber like glulam, CLT, NLT. Could you shed light on this and how engineered timber stacks up against concrete or steel? Yeah, that's a good question. I'll cover this a lot more in the lecture next week. So I'll give you more detail on that then. So if you're not going to join, then this is a good reason to. There are upfront carbon emissions involved in producing those. In general, when you don't want to just consider like the kind of rates of carbon on a per kilo basis, because if you do that, what you'll find is actually concrete is probably the lowest carbon material. But actually, a kilo of concrete is not used in the same way as a kilo of steel or a kilo of timber. So you have to kind of look at it on a grid basis. You look at the functional equivalent of, okay, if I were to design this bay of my building or this roof structure in steel, and if I was to do the same design that performs in the same way using concrete or using timber, then that gives you a much better idea of like which one is kind of the best or the lowest carbon option, I suppose. So you want to basically do equivalent designs in your 3 different materials, then use things like the iStruct tool to measure the impacts of those, and then you'll actually get like a more informed choice or more informed idea of which one's better, or at least lower impact. And when it comes to timber and the actual emissions of manufacturing timber, you're totally right. So if you specify engineered timber instead of just like sawn timber, the process of, for example, gluing CLT or kiln drying actually uses quite a lot of energy. There's also adhesives involved as well. And generally the kind of upfront carbon impacts of using manufactured timber or engineered timber instead of just sawn and dried timber is probably double. So if you can use locally sourced timber that is processed as little as possible, and ideally used in kind of efficient systems, so not like solid floors, but if you're using like a cassette, so you're putting the material in the flanges where it's most efficiently used, that's probably the lowest carbon way of designing a floor, for example. And floors are where like 90% of the carbon in structures is anyway. So yeah, hopefully that kind of answers your question. But yeah, I'll go into that in a bit more detail and the kind of material impacts in the lecture next week. Yep, I can circulate a copy of the slides as well afterwards. That's no problem. And it's all recorded as well, so you can always watch it back. Great. Any more questions for now?
Sorry, just on the back of that, of your answer there, Tom. We've tried to look at exactly what you've just said internally. However, we found it's quite difficult to just turn a concrete building, say a flat slab building, on say a 6 meter grid or a 7.5 meter grid into an equivalent steel building, because you wouldn't use the exact same grid, and likewise for timber. But as you said, the only way to kind of compare apples to apples, you have to do that. But say you were to just click your fingers and change it, maybe for steel you'd go to a 9x12 grid, but then that's an office. So again, if you're looking at a resi building, which you probably wouldn't do steel anyway, unless it were modular. It's very difficult, and as you said, to do that comparison, because then what you'd actually find is that concrete's actually good. So whereas people go, oh, actually, we just simply don't use concrete, and that automatically makes things better. It's actually not. If you turn it into a steel building, it's actually like hundreds of times worse. So how do you propose getting around that? Because it's almost that you need to add in more parameters to compare rather than just same box building, if you like. It just doesn't work with the different materials. So it's been very difficult for us to kind of come up with an internal comparison in order for us to use as a USP for clients, because it's just difficult. I don't know how else to put it. It's something that we're looking at.
No, I think you're not alone in struggling with this. So so Evo, for example, we first of all reduced the grids as much as we reasonably could for an office space. So it's 6x9 grids for the Evo building. And actually, you know, the architect was quite happy with that. The client was quite happy with that. It's a kind of perfectly functional space. And if you can get your spans in the short direction down to 6 meters, then that really kind of unlocks a lot of timber options. So like cross-laminated timber floors. You can get cassettes which span a bit further. So if you go for like a cassette system, then you can potentially go up to like 9 meters quite easily with that. And then you might need like some steel beams or something for your downstands rather than timber, because your glue down beams get quite large as well. So then that kind of has the next outcome from that is that the overall building height gets pushed up a bit because your floor zone, your structural zone is now a lot thicker. So you have to think about, okay, how can I do that cleverly and integrate the MEP services within the structural beam depth, for example. So yeah, there's a lot of trade-offs here, and it's a tricky design process to kind of like weigh up all these different things and make sure that everyone's happy with the kind of compromise that you've met with it. But yeah, I appreciate that it's a challenge. But fundamentally, before you even pick a material, the key thing is like, how can I, whatever material you use, you say, how can I use less of this? Can I get away with cutting even just 10 mil off my slab thickness? I think most people could probably do that on pretty much all their projects, and that would potentially be a bigger carbon saving than your entire lifetime's personal emissions. So like, it doesn't matter if you go vegan or stop flying or whatever. If you've cut 10 mil off your slabs, you're probably there already. So you know, it's really kind of like simple stuff like that, because we have such a massive influence on projects potentially. And then once you've done that kind of reduction as much as possible, maybe even made the building smaller, you know, does it need to be 8 stories? Could it be 7 stories? Would the client be happy with that? If you've cut a whole floor off the building, then potentially that's a significant environmental benefit there. So you do all that first, and then you go, okay, what materials would work best for this particular configuration? Can we kind of tweak it? Now we know we've got maybe some reclaimed steel from another local project, or you know, if we want to use concrete for the foundations, how can we kind of build that into the design and tweak it a bit to fit that material best? But the material choice is that, you know, it kind of comes like towards the end of this process, really.
Okay.
Yeah.
Okay.
All right. I thank you for that, Tom. I don't see any more questions. So let me just say thank you for the presentation. It was very interesting. I know a lot of engineers are interested in calculations, so hopefully next Tuesday when you present the calculations and the carbon calculator and stuff, persons will get a bit more insight into the calculations, the embodied carbons in various materials. Yeah. All right. So thank you everyone for joining us. Have a good day. Tom, thank you very much, and see you next week. Bye.
Thank you.
Bye,
See you
everyone.
next
Great.
week.
Thank you,
Cheers,
everyone.
Tom. Thanks a lot.
Thank you. Bye.
Thank you, Tom.
Cheers.